So I'm going to present you a joint work with Ulysse Chabot and Frédéric Magniez about witnessing Wigner Negativity. You've heard today about phase space, formulation, etc., so that's quite handy for me. But I'll still introduce what is a Wigner function. So here we work in the context of continuous variables. So we take H, the Hilbert space, to be infinite dimensional, and it's equipped with a countable orthonormal basis known as a Fock basis, or sometimes called the photon number basis in the context of optics, which is this ket n here. And what you have to know basically is that a quantum state can be equivalently represented by its Wigner function in phase space. So if I take any quantum state represented in the Fock basis, I can equivalently represent it by a quasi-priority distribution on R2 for all points in R2. And by linearity, I can express the Wigner function of rho by the sum of Wigner function over elements KL. And I only give you the Wigner function to give you an example of a Fock state, one Fock state, n, not the element KL, because that's what we'll need later. And for one Fock state, the Wigner function is given by this formula with a decreasing exponential and a Laguerre polynomial of degree n. And you see here, interestingly, that it only depends on the moduli squared of z. And so that's why for Fock states, the Wigner function will be phase invariant or rotation invariant in phase space. Okay? And so I give you here, to picture what it is, some Wigner function for a few Fock states. So you see that for the vacuum state, ket0, the Wigner function is positive. It's a Gaussian state, actually. And for all other Fock states, and actually any Fock states greater than, for n greater than 0, the Wigner function is negative somewhere. So the Wigner function will still sum to 1, so that's nice, but you can have some negativity. That's why it's a quasi-priority distribution and not a priority distribution. Okay, let's move on. So now the motivation. Why would we study Wigner negativity? Well, there is a result that says that if you want a quantum speedup, negativity of the Wigner function is necessary. So if you take a computation with the preparation of a quantum state and then you apply CPT P maps on the state to get your computation and then a classical outcome, there is a result by Mari and Isaac back in 2012 that says that if all elements here can be represented by a continuous, by a positive Wigner function, then your computation can be simulated classically efficiently. And so what we mean by the quantum, the Wigner function of a CPT-P map would be given, for instance, by the Chaire matrix. Okay, so that's the motivation. So, yeah.
So what's the restriction? Is it on the CPT-P map or on the states that you have as an output?
So this is very general. So basically, you can think of it as if the whole computation is represented by a positive Wigner function, then it's efficiently classically simulatable. But if you want to think of it as some steps in the computation, then you would say that your input state has a positive Wigner function, and then every CPT-P map can be represented by something that has a positive Wigner function, and your measurement also has something that can be represented as a positive Wigner function, if you want to think of it as some small steps in your computation. Is that more clear?
Yeah, what does it mean for the operation to have, like, the point is...
So if you have a CPT map, you take the Chaire matrix, and
okay.
Yeah, that's right. Another motivation is that in discrete variables, we have a link between something very non-classical, known as contextuality, and negativity of the Wigner function. And we are currently trying to extend this link with Robert and Ulysse to the CV realm, so continuous variable realm, but for now it only holds for discrete variables. And the last motivation is that it's quite hard to characterize, say Wigner positive states for mixed states. So for pure states, we know that any Wigner positive non-negative states will correspond to Gaussian states. So if you have a state that is non-Gaussian, then it must be negative somewhere. But and this is Hudson's theorem. But it's only true for pure states. And if you have mixed states, it gets much more complicated. So that's another motivation to study this equation. And so the main question we'll address is, can we get an experimentally accessible witness for Wigner negativity? Okay? So the basic idea would be to do full tomography, right? If I give you, for instance, the state after your whole computation, you can do like full tomography on it, and you will be able to reconstruct the Wigner function, and then you will be able to say if the Wigner function is negative. But the problem is that it's very costly in terms of experimental samples needed. So maybe there is a clever way to test for Wigner negativity. And a way to do that is to define witnesses big omega. So here is a convex set of states with a positive Wigner function. And the idea is to find witnesses big omega together with the threshold values that you have to compute, which will discriminate states with a negative Wigner function. So you see here that the red hyperplane tells you that if you have an expectation value of your state with your witness greater than the computed value, computed threshold value little omega, then you're certified to be in that area, which is a set, which is including a set of Wigner negative states. So you're certified that your state is Wigner negative somewhere. So this is the basic idea. But of course, you need to define the right witnesses big omega, so a family of those, together with the threshold value that you have to actually compute. If you don't have the threshold values, then it's quite useless. And another thing you want for your family is that you want it to be complete in the sense that if you have any state that is Wigner negative, you want a witness to be able to detect it. So for instance, this witness wouldn't be able to detect a state which lies here, because this is a state that is Wigner negative, but it's the expectation value is lower than little omega. Okay? So what is the family of witnesses we can take? So as I said earlier, the Fock bases have a negative Wigner function, except for the vacuum state. So it makes sense to take Fock states to be our witness. Okay, but you could think of more complicated witnesses. Instead of just asking for a single Fock state, you may ask for a finite sum of Fock states, where you have some normalization constraints on the AK I didn't put, but basically AK you can ask AK to be positive and lower than 1. And at least one of the AK is 1, otherwise you could always find a better witness if you want. Okay, so that's, for instance, a better witness than the one earlier because it can detect more states if you want. And another operation you could do, which is very natural in phase space, is just displacing this witness in phase space. So you add a displacement by a complex alpha. Okay? And so this is the family will be interested in this talk. And so now if I take any state and I compute the expectation value with these witnesses, I find that the expectation value is given by a linear combination of fidelities with the displaced Fock states, displaced non-quantum states, and the Fock states. And so basically you can get rid of the displacement because this is an operation that can be done with a classical post-processing. So basically you can really just look at fidelities between the Fock states and your unknown quantum states. And you can actually compute that quite efficiently for single mode states. And for multi-mode states, you have a good approximation for that because otherwise it scales exponentially in the number of modes. But you have a good way to approximate that with n the number of modes. Okay? But as I said earlier, just defining a witness is useless if you don't define the threshold value associated to each witness. And so that's actually an optimization problem. So you try to find the best, the maximum expectation value of your witness with any quantum state that have a positive Wigner function. So this is the optimization problem we will address. Okay. And so this family is nice because it's a complete family. So we know that for any states that has a negative Wigner function, there will exist at least one witness that will detect it. Here I present everything in the single mode setting, but it can be extended in the multi-mode setting. You just have to take multi-mode notation, but of course it's more cumbersome, so I will just stick to a single mode for this tool, but it can be extended in the multi-mode setting. I say it's easy. It's rather easy to measure experimentally, depending on which witness you take. Of course, if you take a Fock state with photon number 20, it will be quite challenging, but if you take reasonable low Fock states, it can be done in the lab, so that's quite nice. And for multimode, as I said, you can have a good approximation of the fidelity. And the threshold value can be well estimated, and that's what we'll see later. Well, now. No, later. So an interesting observation first is that now if I define, so this is a witness omega together with a threshold value little omega. And the nice thing is that if I violate this bound, little omega, so if I take a quantum state that has a negative Wigner function and that violates this bound, this is a lower bound to the set of Wigner positive states, the distance. And this is actually an operational measure. So this is quite nice to be able to relate the violation of our witness to a well-known operational measure of negativity, which is just the distance to the set of positive states. States with a positive Wigner function. Okay? So now we'll go to the computation of the threshold value associated to the witnesses. So as I said, this is an optimization problem, but first we'll simplify the problem. So instead of focusing on a finite sum of Fock states, we'll just look at the case with a single Fock state. So my witness is just nn, ket n bra n. And the finite sum will be just obtained by linearity, so this is fine. So the optimization problem we look at is just the fidelity with the Fock state n over, so you want to maximize that over every state, quantum state that has a positive Wigner function. But that's still quite too general, or maybe no, I will stay as general, but quite too difficult to tackle that way. So we'll do a first trick, is to apply a random dephasing to the states, the unknown state row here that you optimize over. And if you do that, that's quite nice because it won't change the fidelity with any Fock state, so this quantity will remain the same. But instead of asking for a fully general state, it will just have a mixture of Fock states, so it will be diagonal in the Fock basis, so this is much more easier because you have much less coefficients to keep track of. And crucially, it will not increase Wigner negativity, so it can only decrease Wigner negativity. So if you ask for Wigner positive states, then it won't change this. And so because of these facts, you can just express this optimization problem over states that are phase invariant, so random dephased states. Okay? And so phased of this form, and it will be as general as solving this problem. Okay, so now we'll express actually this problem as a linear program, infinite dimensional linear program. And this is really just expressing rho as this expression on diagonal in the Fock basis. So I want to find a family of Fk, maximizing the coefficient Fn because this is actually this quantity. This is just Fn in the Fock basis. You want your state to be of trace 1 because this is a quantum state, so it requires that the sum of Fk is 1. You want all Fk to be positive because you want your quantum state to be a PSD observable, positive semi-definite observable, so you want Fk to be positive. And crucially, you require that the Wigner function is positive, so by linearity, you require that this quantity is positive over all complex numbers. But if you have a look at what actually is Wk, it's a decreasing exponential, which is independent of k, only depends on the modulus of alpha, and the case like a polynomial, which also only depends of modulus of alpha. So you can express these constraints on C, but you can replace it by a constraint on R plus. Okay. Right. But the main problem to compute this on a computer is that it's an infinite dimensional linear program, right? So you ask for an infinite family of Fk, okay, and you have a constraint that is parameterized for all S in R plus, So, I mean, you can't just put that in a computer and expect to have an answer, because you can't actually code that. So you need some tricks to make it finite dimensional. And basically, we'll focus on constraint C3 and also the family of those FK. So the two tricks you can do are relaxing and restricting the program. So first, we'll see how to relax the program. So as I said, what we'll relax is the constraint C3, the positivity requirement on R+. And for that, I will introduce the space Rm, which is just the span of Laguerre functions. So Laguerre functions are just Laguerre polynomials times a decreasing exponential, okay? And instead of asking for a function to be positive on R+, so this was the constraint C3 previously, I will ask for the function to have a positive inner product with a function, with positive function for Rm. So basically, I take any polynomial, I multiply it by a decreasing exponential. I require that this polynomial is at most degree m and is positive, and I want the inner product to be positive. So that's a bit tricky, but the nice thing is that actually this constraint C3 can be expressed as a positive semi-definite constraint. So I didn't put what's the expression of AS because you will see it just the next slide, but basically you can replace that by a positive semi-definite constraint, and also this constraint makes your program finite dimensional. So basically this is a SDP, a semi-definite program, and you can run that on a computer. It's quite efficient to solve, and so it's quite lengthy, but this is basically what you obtain after using the trick I put. So this is basically the infinite dimensional program that I relax, and by relaxing it, it becomes a finite dimensional program that I can plug into the computer. And so later the question I will ask, so of course this program depends on M because it depends on the truncation you make in the space Rm that I put. And the question I will ask is this hierarchy of program converging to my initial program? Okay? But before that, so this is actually giving me an upper bound on the program because this is a relaxation. I optimize on a set that is actually larger than the previous set, so I have an upper bound because this was a maximization program. And before proving the convergence, I will introduce a restriction. So instead of optimizing on a larger space, I will optimize on a space that is smaller. And of course, this will be a lower bound. And the restriction is somewhat more intuitive. Instead of asking for an infinite family of FK, I would just truncate the family and have a finite family. And the nice thing is that if I do that, these constraints, which basically tells me that I take any function, any square integrable function, and I ask the function to be positive, I can replace that by asking for a polynomial of fixed degree m times an exponential, a fixed exponential, to be positive. And okay, I can factor out the exponential, and I just ask for a polynomial to be positive. And asking for a polynomial to be positive, if it's univariate, it amounts to finding a sum of square decomposition, and a sum of square decomposition is just a SDP problem. So again, this is an SDP if I do this restriction. And it's finite dimensional, so I'm happy I have this program, which is a restriction, so it gives me a lower bound on the initial program I was looking for, the initial threshold value. Okay. And so now the question again is, does this converge to my initial program? And so this is the main result of the paper is that these hierarchies actually converge, but there is a small trick, is that the hierarchy I presented, the last one, the restriction, it actually converges to the same program, but instead of expressing it into the space of square integrable function, it's expressed in the space of Schwartz function. Okay. So to prove that the upper hierarchy first converges into the space of, it converges to this program LPN. So this is what I'm asking. What we'll show is that this program has a compact feasible set. So feasible set, yeah, maybe I need to define that. So you see here that you have this quantity which is your objective. You want to optimize this Fn under these constraints, right? So this is the bunch of constraints you have. And if you have a solution that respects all the constraints, you will say that your solution is feasible. And if you have a solution that strictly satisfies all constraints, so you ask that if you have an equality, it's strictly satisfied, and you have a strictly feasible solution. Okay. So the first element is to say that your feasible set of your SDP is compact, and if it's compact, you can extract an optimal solution for each SDP. So we know that we have an optimal solution for each rank of the hierarchy. The next step is to just perform diagonal extraction on all SDPs, so for all rank in the hierarchy. And then on the constructive solution obtained by diagonal extraction, you show that it's a feasible solution for LPN. But if you look at the graph, so basically you extract a convergent solution for that, which is feasible for LPN, but LPN is a maximization problem. So if it's a feasible solution, it means that the limit of this lies below this, because it's feasible for this program, and this is a maximization problem. And of course, you have straightforwardly the converse inequality, because this is an upper bound program. So actually, in the limit, the two values are the same. So that's the converging part. Okay. And for the restricting the hierarchy, so the lower hierarchy, you ask the same question: does that converge to little omega n? And actually, not quite, because if you do the same trick, the extracted solution may not belong to the space of square integral function. That's a shame. But what we found along the way is an analytical solution, a feasible analytical solution of the problem LPN. And how we did that? Basically, we just run the hierarchy for a few steps, M, and we looked at the table, like a bunch of numbers. We intuited what would be the right denominator to have just a sequence of integer. Then we went to the OEIS website, you plug the sequence, and then, well, the first few terms of sequence, and gives you back the sequence it allegedly belongs to, so that's quite nice. And from that, we deduce that which would be the analytical sequence, the analytical feasible solution for all n, okay? But that's quite not finished yet, because, okay, you have something you think is a feasible solution, but you actually have to prove it. And this is quite hard, because you ask for decomposition in the Lagarde basis to be positive, and it's very hard to characterize. So basically, you have to use something known as a Zeilberger algorithm, which just it allows you to prove that sum of binomials are equal, and it just does that by finding a sequence this sum of binomials should satisfy. And if you have two sums of binomials that obey the same sequence, the same recurrence relation, and they are equal for the first few terms, and you know they are equal. And with that, we were able to find a sum of square decomposition for our allegedly feasible solution. And because you have a sum of square, you know that it corresponds to a positive polynomial. So, okay, this is really a feasible solution. And what's nice is that at first we saw this is quite hard, but this is quite useless. And it's not useless because this feasible solution, it allows us to know that the extracted solution here, okay, it may not converge in the dual space of L2, but it will converge in the space of tempered distribution. So the space of tempered distribution is just a space of, if you want, distribution with slowly increasing coefficients. Okay. And so with that, we introduce a formulation for the infinite dimensional program, not into the space of square integrable function, but into the space of Schwartz function and the dual space, the space of a tempered distribution. And we showed that actually this lower hierarchy converge into the Schwartz space. And now if we want to close the gap, so closing the gap is just showing that here it's actually the same values, the optimal solution expressed into L2 or in the Schwartz space. Well, we have these inequalities because by weak duality and also by the fact that expressed into the short space, this is a restriction of the initial program. We know that we have strong duality between our program and dual program expressed into the space of L2 function. And the conjecture, which I'm trying to prove currently, is that actually the program into the expressed into the short space have the same value than the program expressed into the space of L2 function, but it is not quite simple to prove that. Okay, so for now we still have a small gap between the two, but it's not a main problem numerically because it's still a lower bound and upper bound. It's just a convergence of the lower hierarchies that might not be ideal. So now how to use the hierarchy of SDPs. So first, you have to choose a Wigner negativity witness. And in the paper, we have some heuristics to finding a good witness, and I can spend some time talking about that later. But once you choose a witness, what you do is you take the hierarchy of SDP we provide, run them as high as you can in terms of the rank M, and you get an upper bound and a lower bound. Then you, for an experimentalist, you go in the lab and you produce your quantum state and you compute the expectation value trace of rho omega. So you get some estimate and you can compute that efficiently in the lab. Okay? And then you compare this to the values you computed on your computer. So if the expectation value is larger than the threshold value, then you know that your state is Wigner negative somewhere. And if it's lower than the lower bound, then the only thing you can say is that your witness is unable to detect Wigner negativity. And if it's between the two, then you're unlucky and you have to try to run higher and higher rank of the hierarchy to have better precision on the value. Yeah?
So, yeah, the bigger witness, like the witness that you find is for a state, for a specific state, or is it a general thing?
So you have a family of witnesses, and so now you have to kind of fine-tune what witness you will take for each state. So if you run a computation and you have no idea what your state is, this can be quite challenging, but you can just try random witnesses. But then if you have some idea of what your state should look like, then you have some idea of what witnesses are actually good witnesses. I have some examples after.
But then do you need a classical description of your state, or some idea of the classical description?
Yes. Okay. First, I just mentioned a numerical issue of using the hierarchy is that you use Laguerre polynomials. And if you look at the coefficients, the leading coefficients of Laguerre polynomial 10 is 10 to the minus lower than the Laguerre leading coefficient of the first Laguerre polynomial. And so this is quite challenging if you implement that on like current SDP solvers. Because, I mean, if you go to rank 10, it's not like going very high in the hierarchy, right? So you won't have very good values, but it's still a problem, right? So instead of using like any SDP solver, like even the best one, we use a much lower solver, which is known as SDP-HGMP, but it's much more precise, so it will deal with numerical issue with very high precision, and it tells you to go very high in the hierarchy compared to standard solvers. So now what we did is we just computed the threshold value associated to witnesses as just single Fock state, for a Fock state going from 1 to 10. Okay, so you have a table like that. And now if you take like your quantum state and you compute the expectation value with Fock state 3, if it's larger than these quantities, then you know that your state is Wigner negative, as I said. And another example, so I said that our techniques may be generalized to multimode, okay? And so now the question is, what happens if I take a low C 1-1 state? So this is a low C 1-1 state parameterized by the loss parameter eta. And of course, if I know that I have a low C 1-1 state, or if I try to create a 1-1 state, and I know that my setup is a bit low C, my guess is that it will be close, or I want it to be close to 1-1. Okay, so my witness would be 1, 1. So now I can compute the threshold value associated to the witness 1, 1, and I see here that in red this is the upper bound, and in black this is the lower bound. And here in blue you see that you can detect Wigner negativity up to this regime of loss. Okay? And here you have two curves, because I said that in multimode it might be not efficient to compute the fidelity. So in blue this is the efficient way of computing the fidelity, and in yellow this is the exact computation of the fidelity, which might not be efficient in the number of modes. Okay? So to conclude, we've introduced a complete family of witnesses with a multimode generalization as well as single mode. Experimentally, you can efficiently estimate the expectation value with your quantum state, with our family of witnesses. And this gives an operational meaning, because the violation of the value of our witnesses gives a lower bound to the set, to the distance to the set of Wigner positive states. So this is quite desirable. Together with a witness, you need to compute the threshold value, and it can be done numerically with two hierarchies, an upper hierarchy and a lower hierarchy that gives good upper bounds and lower bounds. And we also provide a repository to play around with the hierarchy if you're an experimentalist and you want to witness Wigner negativity. And with that, I conclude.